Okay, so what we're going to do now is go through several websites that show air pollution and fires measured by satellites. This is the topic of this lecture, and earlier I gave an introduction to the topic through several PowerPoint slides. And what we'll do now by going through these various sites and the displays on them is illustrate some of those points that we just went over. So the first site, of course, is this fire and smoke map from AirNow, which we've been looking at before we got into satellite measurements of air quality. We've been looking at this to look at these ground monitoring measurements of PM 2.5s. And these are these triangles and circles are various stations that we've talked about before. What I want to point out now, you see this gray area here. This is, all this gray hatching that kind of is surrounding certain areas on the map. This, if you were to look at this is indications of smoke plumes being detected. And the manner of detecting these things is the remote sensing that we're going to talk about. So let's go ahead and go to another site now called Aerosol Watch. And you can see the URL up here, and I will make a list of these in the PowerPoint as well so that you see where these sites come from. But this is a site called Aerosol Watch that updates the display of various remotely sensed air quality quantities every 10 minutes. Okay, so let's, I'm going to toggle off some of these for now and just to lead up to it. And what I've done is I've set the timestamp here for today, the 24th. You can, hitting this calendar, one can go back in time and look at other images, but what we're looking at now is today, September 24th, 1641 UTC. If you were to subtract 7 from that, you can convert that to 9:41 local time in the morning. So this was an image that from a few hours ago. And if you see that if I were to pump forward, step forward through these toggles, I can jump through every 10 minutes as the site says it would do. Okay, so what we're looking at now is just the clouds being detected by the what looks like to be the GOES-17 geostationary satellite, I'm imagining. But what we'll do now is let's go and look at some air quality measurements now. So I'm going to go backwards in time so we can look at a full animation. And I've queued this to start at 7 in the morning, about 14 UTC. And this is, you can see it's darker now because the sun is low in the sky and there's not a lot of sunlight being reflected off the clouds and things that we can see. But as we move forward in time, the sun comes up and we see things. So let's go back again. And what I'm going to do now is I'm going to toggle this GOES-17 layer. Remember, this is the geostationary satellite that I mentioned what geostationary satellites were in the lecture. And I'm going to toggle AOD. This is aerosol optical depth. This is one measure of air pollution that satellites can detect. And what it is, it's the total amount of particles or aerosols in the column of Earth that extends from the surface to the top of the atmosphere. Because the satellite's going to look down over the total atmosphere. It can't distinguish very easily, if at all, where in the vertical column the pollution is. So it just gives you the total amount in the column. So let me go ahead and toggle that. And you see that some images populate. And so what I'm going to do now is go forward. This is at 7 in the morning. And when I'll go through and go forward in time, and you can see that we see very distinct detections of aerosol optical depth as detected by the GOES-17 satellite. So let's go ahead and we're right now, we're at, let's see what stops. And I can advance forward all the way to current time. And so what we're seeing here is, if I go back to our fire and smoke map, you see this plume of smoke being detected downwind of these fires that are in the southern Sierra Nevadas, Sequoia National Park. And now we see, if we can see more literally what that is. It's the aerosol optical depth measured by, in this case, the GOES-17 geostationary satellite. So what's happening is this is a visible detection. So sunlight is reflecting off the smoke particles in the column of air. The reflected sunlight from the smoke particles is going back to the satellite sensor, and the sensor is cued to be able to send back to the Earth the amount of reflected radiation the satellite received. That is then converted to an aerosol optical depth through various more sophisticated methods that we won't get into. But anyway, this is aerosol optical depth. You can see several centers here. We can see the center that's of smoke being blown downwind of the fires in the Sierras. If I were to zoom in more and kind of go up here, here's another fire detection area in the just south of Redding in the Northern California. Let me go back to our map here and zoom in. You can see it's what we're looking at is this area right here of smoke being detected by the ground monitors. And you can see this gray hatching here. That's an indication of what the GOES-17 is picking up through aerosol optical depth measured by the backscattered visible light detected by the GOES-17 satellite. Okay, so that's this. You can use this site, this Aerosol Watch, and again, I'll give you the URL to go back in time. If you go back for like a week or two ago, you'll see very strong detections of when the fires are more widespread. One thing you'll also notice that I forgot to mention, but I'll mention now, is that this splotchy kind of pattern is because two things. One is that the satellite cannot detect any aerosol in the column if clouds are obstructing the view. So any place where you see a cloud, you're not going to see any AOD or aerosol optical depth detection. Elsewhere, there's portions, even if there's no cloud, where the reflection of the sunlight off the surface itself is contaminating the signal so that to the point where AOD cannot be detected. So they don't color those areas as well. So this is one of the advantages of satellites, is that you can detect things where monitors aren't. One of the disadvantages are one of the things that prevents that from happening everywhere is the presence of clouds and sometimes the effects of reflection of sunlight off the ground contaminating the signal. So aerosol optical depth, this is one thing we talked about in lecture, and here's an illustration of it through GOES-17 detection. Okay, so let's move on now and let's look at one more site. And we're going to look at this JSTAR mapping site, again, a NOAA site. And right now I don't have anything populated on the map. I'll just kind of pan it over a bit now. But you see on the left here, there's some controls. And so what I've done is I've queued this to start on the 14th of September. These are not going to be hourly images or 10-minute updated images. These are now going to be daily snapshots detected by two polar orbiting satellites, Suomi and the Sentinel FP satellite released by the European Center. Suomi is a NASA satellite, the Sentinel is a European satellite. And on both of these satellites, there's things that we can look at. There's instrumentation on these satellites that are relevant to fires and air quality. So we'll start with the Suomi, and I'll show this. And what I'm going to show is something called fire radius of power. And you see these little orange dots populating the country. And I'll go ahead and zoom in on California now so we can get it. And what's happening here, and this is fires themselves, not the smoke from the fires, but the fires themselves. What the satellite is detecting is the heat radiation emitted by the fires. And this is, fires are very hot. So I guess two things can, you can see the visible light, but you can also see the heat itself from the fire, um, releasing radiation to the satellite sensor where you can detect where the fires are. So fire detection is one of the other things that satellites can do. It can detect where the fires are. And if I can jump forward in time, you see this updates every day. And one can see where the major fires are. So I can zoom in on some of these. Just in LA County, we have this Bobcat fire that's been going on now for a couple weeks, and it's been a major incident. Here's our fires in the Southern Sierras, kind of populating on there. And then in Northern California, we have some that we're detecting. Let me go forward a few days, see if what else shows up here. Okay, we'll stop here. You see the color coding is orange and reds. You can see on the lower right here, they color code the fire radiative power in something called log 10 of megawatts of infrared energy released by the fire. And one of the things here is that oftentimes other things can release infrared radiation that the satellite can pick up that may not be a fire. And so anytime anything like that is cued, they color code it. For example, if there's a volcano or emitting, they'll want to cue that. Gas flares, oftentimes refineries and things like that have flares that release, that burn off excess gas, and it shows up as a fire. And they'll want to indicate that so we don't confuse that as a fire, a wildfire, for example, and so on and so forth. So any place you see oranges, the yellows and reds, though, are actual wildfires that are burning, and you can detect that. Okay, so that's one thing that you can see. Let's move on to the second thing, and this is air pollution related directly. I'll show something from the Sentinel FP, and what I'm looking at is carbon monoxide being sensed by the satellite in the column. And you can see here, there's color codings going from blue to red. Notice how this is being measured in 10 to the minus 1 moles per meter squared. What that is the number of moles of molecules per square meter. And if you remember back from lecture, another way we measure satellite air quality is in the total mass of pollutant in a column extending from the surface to the top of the atmosphere. One way to do that is in moles per meter squared. So anyway, that's the color coding and the unit of measurement of this. And again, you'll see exactly what we expect is where the fires are. We see a lot of carbon monoxide being released and pumped into the atmosphere. Carbon monoxide is a product of combustion and therefore will be released when there's a fire. And so all the main centers of fires are also showing up as carbon monoxide. So I'm going to zoom out now. And one of the neat things that you can do with this, since this is our daily snapshot, we can go through day by day and look at carbon monoxide from a lot of the fires in the Western US being moved by the wind eastward across the country. So let me do that. I'll just kind of show you that here. If I just go backwards in time and start at a certain date and we can track forward, we go around here. So maybe one more, let's see here. Yeah, this is a good place to start. So this is about a week ago on the 13th of September. You see there's a lot of fires in the Western US, and a lot of this, you can see this, smoke from the fires is showing up as a carbon monoxide signal moving with the wind across the country. I'll just animate this so you can see that literally. So this is from September 11th, where we had a lot of big fire days, and there was offshore winds blowing the stuff away from the coast. And if I move forward in time, the 12th of September, the 13th of December, the 14th of September, you can see all this stuff is kind of moving and wafting around the country as the wind blows things from west to east. It's as far into Canada, as you can see here. So that's another thing, way you can use satellites is you can look at the carbon monoxide, this time from the Sentinel FP tropomi products, showing carbon monoxide. One final thing that I'll show that's also on tropomi is not just carbon monoxide, but is nitrogen dioxide. So I'll show that. And what do we see? Well, nitrogen dioxide is also a product of combustion. However, it doesn't have the same signal as carbon monoxide does. We can compare on the 18th of September the nitrogen dioxide signal, which, as you'll see, is much more centered around the urban areas. I can go in way in, and this is Los Angeles right there. So a lot of the nitrogen dioxide that the satellite is sensing is centered on the urban areas. Whereas if I look at the carbon monoxide itself, it's more showing up as the fires. So just, there's a difference here. We want to understand what's going on. I can go zoom out a little bit more, and you'll see that the nitrogen dioxide also shows up in other urban areas. Here's like the Minneapolis area. I think that's Minneapolis, St. Paul, maybe. Here's the Chicago metro area right here, and a few other areas where, if I can jump forward. Yeah, here's Chicago right there. So nitrogen dioxide is a product of combustion, but since it is so reactive, nitrogen dioxide reacts out of NO2 very quickly, that the signal is going to show up very much centered on where the emissions are. And by the time that stuff blows elsewhere, the nitrogen dioxide has reacted, so it's not nitrogen dioxide anymore. It turns into other things through the chemistry. So we only see the nitrogen dioxide where the emissions are, not so much where the stuff blows, because by then it's reacted out. So because of that, the satellite detection of nitrogen dioxide is very good at identifying locations where emissions occur. And we've differentiated before between emissions and concentrations. Emissions come out of sources. Concentrations are what you are exposed to in the air and what blows in the air and moves around in the air. So whereas carbon monoxide, you can track things as it blows downwind from the source, because carbon monoxide is not as reactive as nitrogen dioxide. Nitrogen dioxide, on the other hand, is only going to show up very close to the sources. Because of that, NO2, nitrogen dioxide, is detected by satellites, is a very good indicator of emission locations, whereas carbon monoxide is not just emissions, but also the concentrations that blow downwind. You can track it in space as it moves around. So these are some things that satellites detect as far as air quality. Again, to review, we've looked at carbon monoxide, we've looked at carbon and nitrogen dioxide, we've looked at fire detections through fire radiative power, and earlier we were looking at aerosol optical depth as measured by the geostationary satellites. Okay, so with this, I will stop. Take home with you the main points that were presented here with respect to aerosol optical depth, fire radiative power, carbon monoxide, and nitrogen dioxide, and how each of those is detected by satellites, and what are the distinguishing characteristics of that satellite detection with respect to each of those four pollutants. Those are the things that I will be looking for and asking questions on the exam to check understanding of these topics. Okay, I'll break here. Have a nice day, guys. Bye-bye.